Section 8 deals with acid chlorides, okay? And there's pretty much only one way you can make acid chlorides as presented in the textbook, and that's a pretty good reaction, fairly universal, okay? So if we have something like benzoic acid, if we treat this with thionyl chloride, we can make benzoyl chloride. Okay. From this reaction, we produce sulfur dioxide and hydrogen chloride. Okay, so SOCl2 is called thionyl chloride. It's fairly reactive, reacting with water from the air, and it's pretty reactive chemical to handle. It's very corrosive. So let me show you the mechanism, okay? So we don't worry too much about the SO2 and the HCl. We, of course, are focusing mainly on this reaction here, which is the main synthetic transformation, okay? Now let me show you what the mechanism looks like. So we've got a couple of different nucleophiles here. Now, in general, most of the time you want to use the carbonyl oxygen to do the attacking. It's a stronger nucleophile. And so let's draw out the thionyl chloride. So these are weird inorganic chemicals that you may not have seen before. So we'll draw the Lewis structure with all the lone pairs there. And so what you want to do is, in general, use your lone pairs. But anyways, we'll take lone pairs of this oxygen atom here and attack the sulfur here, okay? Now it is possible first, well, this is the mechanism proposed in the Klein book. So we'll just write it out, okay? So first you have attack, all right? And we draw out what we have there. Add all these lone pairs in. Okay, and we have a doubly bonded guy here, okay? So, and a formal charge of positive, okay? So, okay, I forgot. I mentioned that I would tell you if these reactions are acidic or basic. I was under a faulty assumption that most students would recognize that this is under acidic conditions because you're producing hydrogen chloride, okay? So what we have here is an acidic reaction condition. Recall again, we do not want to have any negatively charged oxygen atoms when we have acidic reaction conditions, okay? So all of these oxygen atoms, generally speaking, should be neutral or protonated. And you can see here how we're breaking this rule in the very first reaction mechanism, all right? So that's an O negative, all right? So we do have the positive here. Now, what happens at this stage is that we are going to kick off our leaving group, okay? So kick off the chloride. And that's why I like doing SN2 for the very first reaction mechanism on the sulfur. Either way, it would mess up one of our two rules. So anyways, we have this kind of intermediate here, okay? Well, we're not quite there yet. Let me take chloride, and we'll use that as a best alternative to a basic thing we have. And so that's a deprotonation. Okay, and I'm going to highlight here what our leaving group is. Sometimes we can get lost with all of the details, but basically what we're doing is we're converting this guy here, which is a poor leaving group, into this guy here, which is an excellent leaving group. Okay, why is that a good leaving group? Well, let's take chloride and let's do the nucleophilic acyl substitution. So remember, we can't do SN2. We've got to attack this and go through this intermediate. Okay, so we have this tetrahedral intermediate here, and again we have this negative charge on the oxygen. Okay, and what we want to do now is to kick off the leaving group. So this is going to collapse, and we're going to form through an elimination process the acid chloride. So this is where you form the acid chloride. And we form this byproduct which I won't draw all the lone pairs in there, but that goes on to form sulfur dioxide and chloride. So that's where the sulfur dioxide is produced. In this step right here, you form the hydrogen chloride. So it's a very weird mechanism. This is mechanism 21.2. Okay. I personally don't require my students to memorize this reaction, but I just wanted to point out what happens, okay? It's quite lengthy. It's quite intricate. Okay, you first have attack of the carbonyl oxygen or the pi bond on the thionyl chloride. This intermediate collapses, and you have chloride deprotonating and then attacking, and finally you kick off sulfur dioxide and hydrogen chloride are formed in the reaction, okay? So this is how it works. The main key point here is that you can grab any old carboxylic acid you want. You can treat this with thionyl chloride. And you form your acid chloride, okay? So that's the main reaction that you need to be aware of, okay? This reaction here. Now, hydrolysis of acid chlorides can be done, okay? So we'll call this reaction 1. Acid chlorides can react with water. Drew it out there so we can show the mechanism in a bit to give you acid chlorides react with water to give you the carboxylic acids back again. So if you're not careful when you make your acid chloride, it might get moisture into the flask from the air and slowly convert back to the carboxylic acid. So how does this reaction work? The acid chlorides are just so reactive, they break a lot of the rules, but you always have this tetrahedral intermediate, okay? So water is going to directly attack. The chlorine there is just so electronegative, it's quite electron deficient, okay? you get the tetrahedral intermediate. And then what happens at this stage is that we have chloride being expelled out, okay? Okay. You always want to kick off the leaving group, usually first, before you do any acid-base manipulations. So here we're going to expel or eliminate the chloride, and we're going to form the protonated carboxylic acid, okay? So there's a extra proton here, so that's super acidic. And you have chloride floating around. Chloride is now going to deprotonate. And that's going to give you the carboxylic acid and hydrogen chloride. So it's AED for the curved arrow reaction mechanism. Okay? Now, fumes of hydrochloric acid normally are produced. It can corrode metal equipment in your fume hood and come into the ducting and so on of your building, and it can be quite noxious, right, to be breathing those things. So oftentimes we add pyridine to the reaction mixture to soak up any hydrochloric acid that's produced. This is described on page, in the Klein's textbook as well. So what we normally do is if we have a carboxylic acid chloride, let's put, I don't know, some interesting functional groups here. And if we treat this with water, we oftentimes add pyridine on the bottom. PYR is pyridine. And that, remember, is a six-membered hetero-aromatic thing. Okay, so it can, it's a base. All right, it's a base. And so this reaction is going to give you the carboxylic acid. All right, that's all. We're not going to draw anything special here, but I do want to mention that that's auto-detecting, that's an ellipse, that's fine with me. So what is the pyridine doing? Well, when you have hydrochloric acid being produced, rather than it bubbling out of your reaction mixture and ruining your lab, pyridine at this point comes in and absorbs it, okay? It soaks it up. It's like a sponge, okay? And that gives you pyridinium chloride. All right, so it's a cleaner way, okay? You wouldn't want to know that there's a company down the street or in your town that's producing tons of hydrogen chloride and just emitting that into the air. That would lead to acidic rain probably, right? So you'd want to know that they're using pyridine to, isolate this chemical and keep it in a waste container or something. All right, so that's the use of pyridine. You'll see that a lot, okay? Particularly when you do alcoholysis of acid chlorides. Reaction number 2. Alcoholysis of acid chlorides. Okay. Please don't get confused by the pyridine. It's just in there as part of the reaction mixture. So if we've got an acid chloride, and we treat this with ethanol, and we'll add pyridine there. The pyridine, once again, is just to absorb any hydrogen chloride that's produced. What we're going to form here is an ester. Okay, so that's the ethyl ester, and you can see that this ethyl alcohol is ending up right here. Okay, and of course you're making hydrogen chloride. We don't worry about balancing these chemical reactions, but technically that's reacted with the pyridine, right? So how does this reaction work? The reaction mechanism is very similar to what we had with alcohols, okay? So in the first step, we're going to have Let me draw it in exactly the same orientation. In the first step, we're going to have ethanol be a nucleophile, okay? So again, acid chlorides are so reactive, you don't need to protonate the carbonyl or anything like this for it to react. They just immediately react, okay? So the ethanol is going to attack and you know, we can add all these lone pairs in here to maintain the octet. And so we have that tetrahedral intermediate, remember? And now what we want to do is kick off the chloride, okay? Kick off the chloride. And then here's where we want to use pyridine. Pyridine is the base. And you might make a note here for yourself. Wait, why don't I use chloride? Pyridine is the base, right? Pyridine is more basic. Probably pyridine does the deprotonating here first, okay? So we'll draw a curved arrow coming from this nitrogen here to give me the ester product, okay? So that's D for deprotonation. All right, so attack, eliminate, and then deprotonate. So those are the three steps for an alcohol reacting with an acid chloride. So keep in mind, many different kinds of acid chlorides could be used. Many different kinds of alcohols could be used. And so be prepared to understand the patterns here, okay? So if I have an acid chloride that looks like this, and I add isopropyl alcohol in pyridine, what am I going to form? So you just need to pay attention to the branching and the number of carbons. So this is a secondary alcohol with 3 carbons, right? And we're going to hook that up to the carbonyl carbon and remove the chlorine and remove the hydrogen. So what you're going to form here is sketch out everything that's there. Okay? Make sure you keep the right number of carbons and branching and all of that. And then here's where that oxygen atom is going to be. It's going to be right here, and then you want to sketch in those 3 carbons with the branching, okay? So we're removing this chlorine and we're removing this hydrogen, okay? So that's how you draw the reaction product. You might have these weird alcohols and acid chlorides that could be shown to you in problems, okay? So that's called the alcoholysis of acid chlorides. I just call it esterification or ester formation, okay? The next thing I want to talk about is formation of amides. Aminolysis of acid chlorides. Okay. What does this look like? If you take an acid chloride, and you add excess ammonia. Okay. XS stands for excess. Okay, that means more than 2 equivalents. What you'll form here is an amide. Okay. You can also do this with primary amines. So for example, if I add 2 equivalents of methylamine to this, I will get the N-methyl amide, okay? Now, I just want to make a point here that we are using excess of the amine rather than using pyridine as a base, because the amines are actually going to be basic, okay? So note, use excess amines, and then which are basic, so we don't need pyridine, which is a base, okay? So bases are nucleophiles, they gave you the amide, and then bases are also, amines are also basic, so they can help soak up the hydrogen chloride that's formed. So this is with an amine, this is with a primary amine, okay? And let's show the reaction with a secondary amine. So if we have a acid chloride that looks like this, we can add 2 equivalents or excess of, let's use diethylamine, okay? So let's use diethylamine. What we'll get there is a amide that has an ethyl group and another ethyl group on the nitrogen atom of the amide, okay? So those are just sketching out some reactions of the aminolysis there. And the book doesn't seem to show the curved arrow reaction mechanism, but let me take the time to show you that, okay? So we'll do this first one. Any of these reactions are going to have the same mechanism, okay? So maybe I'll do the second one. All right, so let's show the curved arrow reaction mechanism for this process here. We're going to add excess methylamine to this, and we're going to form the amide, okay? So what we have first is an acid chloride, which is extremely reactive. So the methylamine has lone pairs on the nitrogen. That's our nucleophile. And that's going to attack the carbonyl carbon and give you the tetrahedral intermediate. Okay, let's go ahead and kick off our leaving group. So we've got the correct, oxygen with the lone pairs as the amide there. But we've got a problem with the nitrogen. The nitrogen has a formal charge of +1. So here, do not use the chloride as the base. Use the amine, which is the base, okay? So I'll highlight that maybe in yellow here. Okay, so you want to deprotonate. And what you form is your N-methyl, it's going to be a butenamide. I won't try to name this one. So it's AED, okay? It's AED. The reaction mechanism is exactly the same, all right? So that's the aminolysis of acid chlorides, okay? So ammonia, primary amines, secondary amines can all be used. Make sure you use 2 equivalents or write excess above your reaction arrow. Okay. Next up, we have reductions. Okay. Acid chlorides can react with lithium aluminum hydride. So remember that LaH is a source of hydride. Okay? So we could have an acid chloride and if I treat this with lithium aluminum hydride, which is excess, always assume lithium aluminum hydride is excess, but we're just emphasizing it that you have more than one, okay? And so what you form from this reaction is a primary alcohol. The mechanism is quite straightforward, and it's a great thing to look at and also review. So the mechanism involves hydride attacking, once again, you form that tetrahedral intermediate. So I'll draw the H in there. Chloride's going to leave. That's our leaving group. And you have an aldehyde. And remember, once again, that aldehydes can react with hydride. Now, we're not going to substitute anything. This is an addition reaction. So hydride adds, and you form the alkoxide. Okay? And it sits there and waits around for you to tidy up your notebook. Now, when you come back and in step 2, when you add water, a large excess of water I might add, this is when it reacts to form the alcohol. Okay, so that's a protonation. We're protonating the alkoxide. So what do we have? We have AE, then AP. Okay, so AE is the new stuff, AP is the old stuff. All right, so the reduction of acid chlorides is straightforward. You always form the primary alcohol. Okay, it doesn't matter what you might have. If you have an interesting acid chloride, let's put an isopropyl here maybe. Interesting enough, okay? And if we add LaH, so just remember, it's always excess, all right? The book kind of makes a point of you writing excess, but I know and everybody knows that it's usually excess. All right, and what you're going to form here is primary, alcohol, okay? So that's all you need to know for this kind of chemical reaction here. It's a pretty simple thing. But remember that hydride can react with the aldehyde, so that's why you form an alcohol, not a carboxylic acid. Now, you might wonder, well, can you use one equivalent? Is there a way to stop at the aldehyde? And people have figured this already out, okay? They use a more fancy reagent that has only one hydride in its formula, okay? You see lithium aluminum hydride, as we saw, has 4 hydrides, okay? And because of these multiple hydrides here, you're going to add an extra amount to your molecule that you're starting with. So what they've decided to use is a mono-reducing agent. Okay? It's lithium triterbutoxy aluminum hydride. So That's a mouthful, but it looks like this. So there's 3 tert butyl groups here. And the development of this reagent took some time, but you know, basically we can just think of it as, okay, well, it has only one H, so it adds only one time. Okay? And when this reaction is written down, it has this form. Okay? So this right here is going to be abbreviated. Like this in the book. Okay? So there's, of course, a lithium ion floating around to counter the negative charge on the aluminum. So there's the lithium, there's the aluminum, and then we have 3 OR groups. Okay? This is an OR group, this is an OR group, this is an OR group, and then at the very end is an H. So the easy way to remember that this is a mono-reducing agent is that there's just one hydrogen right here shown in the formula. Okay? So as an example of this, if we had that molecule I drew before, this guy right here, and we treated this with this guy. So instead of LAH in water, we're using this weird creature and water. What you do is you stop at the aldehyde. Okay? And on paper it works great, but I can tell you in practice results may vary. All right? So that right there is another reaction that you'll need to learn. What are we on? Reaction number 4. Okay? Greenyards also react with acid chlorides. Okay, now let me show you what the form looks like. So if we have a if we have an acid chloride like this, and then we add 2 equivalents of, I'll make it a different color here, R MgX. So I didn't mean to put a parenthesis there. So I'm adding 2 equivalents of this, okay? Or excess. That's step 1. Step 2 is to add water. And what you get here is a tertiary alcohol with 2 additional carbon-carbon bonds being formed. Okay, so this is a carbon-carbon bond forming reaction. You really want to pay attention to that. How does this reaction work? It works just like we saw with lithium aluminum hydride. We have a carbanion, okay? That could be a methyl anion, an ethyl, maybe a phenyl, whatever. Here I'm just going to draw R. So this can attack, okay? This gives you a tetrahedral intermediate once again. Remember, R is a very bad leaving group. The only leaving group we have here is chloride. So that makes a ketone. And I want to keep my colors in here so you can see what's happening. So that makes a ketone. And we know from prior chapters that ketones react with Greenyards. So let's draw that second stage, okay? So here I have a Greenyard now attacking the carbonyl, okay? And here we have no leaving groups, so the intermediate just hangs around there for us to tidy up our notebook. And we, of course, add water after step 2, on step 2, and we protonate that alcohol, and that gives us the final products, okay? So that's AEAP, same exact thing we saw with lithium aluminum hydride, All right, so that's what Greenyards do. Now you might be asking, well, lithium aluminum hydride adds extra amounts of hydride, and there was a way to figure out how to make only one hydride add to it. And here we have Greenyards that just add all of their R groups to our acid chlorides. Is there a way to only use one of them? And the answer is yes. We use what's called a lithium dialkyl cuprate, or a Gilman reagent. Okay. Now, because of the very decreased reactivity of the lithium dialkyl cuprates, they only add once, okay, or substitute the chloride in the acid chlorides. So a Gilman reagent is going to look like this. Okay, strange little thing, right? It's a metal bonded to a metal. And then that can react with acid chlorides to deliver only one R group. So what does that look like? Let's give an example here. If I have an acid chloride, okay, and then I add R2CuLi, that's how we draw that thing, okay? You're going to add only one R group to the final molecule, and it stops at the ketone stage. Okay, don't worry about all the other stuff that's formed there, but that's a pretty neat reaction, okay? So let's discuss the summary now of, so let's talk about all of the different reactions we've talked about in section 8. We've learned 10 reactions here, okay? So the key point here is that the acid chloride is very reactive, okay? It's right here. And we know we can kill it with water to form carboxylic acids. We can add alcohols to give esters. We can add ammonia, primary amines, or secondary amines to give amides, okay? We can reduce acid chlorides in two different ways. We can add lithium aluminum hydride, okay? Or lithium tritert-butoxy aluminum hydride, this crazy looking thing here, to give aldehydes. And we can add or make carbon-carbon bonds by adding organometallic reagents. If we use a Greenyard reagent, we form a tertiary alcohol. If we add the Gilman reagent, we stop at the ketone. Once again, I highly recommend that you make flashcards, maybe of some simple things like this. Keep them in your back pocket and spend 5 minutes, 4 or 5 or 6 times a day throughout the day, just thumbing through them and trying to memorize these reactions, okay? So that's it. Well, let's do some practice problems now. So practice problem 21.18 asks us to remember some things, okay? So many of these are just one-step reactions. So remember again that we have excess. So if you think through the mechanism. Hydride is going to replace the chlorine. That gives you an aldehyde. And then since we have excess, it's going to react further to give you an alcohol. And I'll just draw the two hydrogens in there. Okay? So those two hydrogens came from LAH. In reaction B, we're adding a phenyl magnesium Greenyard to that. So same thing, the first Greenyard is going to kick off the chloride, and that gives you a ketone, and ketones react with Greenyards to give you alcohols. So we need to add 2 phenyl groups to this. One phenyl group will be here. I'll do that in green. Another phenyl group is here. I'll do that in green. It's completely acceptable to draw pH. You can also draw out the phenyl ring with the 6 carbons and the 3 double bonds. In molecule C, it looks like we have some more steps here going on. So what's happening with this reagent? Okay, if you look at the letters here, it has only one hydride. Okay, so it's going to make the aldehyde, and then what we do is we add ethyl magnesium bromide. So that's going to react with the aldehyde to give you an alcohol. All right, so after that's all said and done, you're going to make the aldehyde in step 1. And then I hope you remember the aldehydes and ketones chapter. When you add ethyl magnesium bromide to this, followed by water workup, you form an alcohol with an additional ethyl group added to that carbonyl carbon. And here I'll just highlight where that ethyl group is. It's in green here, so 2 carbons attached to that carbonyl carbon. In molecule D, what do we have going on here? We have ethyl diethyl cuprate, right? So this is the Gilman reagent. We want to replace that chlorine with an ethyl group. All right, so that forms the ketone with the ethyl group there, right? The ethyl ketone. And then what's going on here? Well, we add LAH and water. So remember from chapter 20 that aldehydes and ketones react with lithium aluminum hydride to give you alcohols. So this is going to give you the alcohol here, and we're basically adding hydride. And at this point, I just want to mention that these are the same molecules. So this right here in molecule, the product from C is the same as the product from D. You might look at those again now that you see that. In part E, we have an alcohol and we have an acid chloride. So we know this is going to make the ester. So phenol is a nucleophile. It just attacks like any other alcohol. In part F, we have formation of an amide. So replace that chlorine for the nitrogen. And then think about carefully what R groups are on that nitrogen. There's like a ring, right? So you want to keep that ring intact. It doesn't break apart or anything during this reaction. Okay. Problem 19 and 20 are some good problems, and I'm sure there's other ones in the back of the textbook as well. So I'm pretty sure you've got a feel or a hang of things by now. So we'll stop that here. Okay. So I hope you understand all the 10 reactions that acid chlorides can undergo or be involved in. Thanks for watching.